being outdoors with beautiful colors everywhere? On my days off, I try to enjoy the simple pleasures in life, like nature and painting. Colors have always been special for me. In painting, I use my eyes to gauge colors, which is fine for oils. But you know, we all see colors a bit differently. Some might see this as red, some more as an orange.
Orange. How about a little more on the right? Can we get that?
During the week, I work with color in a different way. As a video graphics artist, TV production demands a certain precision when it comes to color and conceptual interpretation. And a vital part of any production is high technical quality. This includes correct color reproduction, which doesn't compromise artistic license. The key to maintaining this color quality is to carefully monitor a picture signal before it's recorded or transmitted. This is done by using a well-defined test signal with known characteristics, such as color bars. Since we know what the test signal should look like, we can easily see if it has been changed by distortions or impairments. If the test signal goes through the system without distortion, we know our signals will also pass through clean and undistorted. The three most essential pieces of test equipment for video are the waveform monitor, Vectorscope, and the test signal generator. Using a Tektronix waveform monitor, let's quickly review how the waveform monitor works, then we'll move on to the Vectorscope. The waveform monitor graticule is arranged so the vertical IRE markings show amplitude, which is used for level setting and monitoring. IRE stands for Institute of Radio Engineers, who devised this system of measurement. The horizontal markings are used for timing measurements. Remember, a TV picture is made up of 525 lines, which are split into two fields. Each of the horizontal lines scans one field, left to right, from top to bottom. Upon completion, the beam returns to the top and scans the next field. This occurs 30 times a second. Every line has a negative going synchronizing pulse called the sync pulse. Here's how the sync pulse looks on the waveform monitor. On the Vectorscope, it is simply seen as a dot in the center of the screen. And on the picture monitor, it's this black bar, which would normally be off to the left of the screen, out of the viewer's sight. This sync pulse sends the beam back to start another line and is contained in the signal's horizontal blanking interval, which is the short period of time between the scan lines. So the serrated horizontal line is the scale which shows you where the picture beam is at any incident in time, while the vertical markings measure the amplitude of the signal. Let's take a closer look at the waveform by using a color bar test signal. Each bar represents luminance voltages. The bars are arranged by luminance levels from highest on the left to lowest on the right. Each bar also represents a color: white, yellow, cyan, green, magenta, red, blue, and black. Waveform monitors are particularly useful for setting proper video levels. Start by making sure the blanking level is at 0 IRE. Then check to see if the 100% white reference level lines up to the 100 IRE graticule line. The black level should be 7.5 IRE. The waveform monitor allows us to observe luminance levels, much like a light meter for a photographer. If the picture is too bright or hot, the monitor would look like this. If the picture is too dark, it would look like this. Again, adjusting the levels to fall within the 100 IRE and 7.5 IRE would take place at the video source. Here's how a black and white picture would look on the Vectorscope. It looks this way because Vectorscopes are used to measure the chrominance or color portion of the signal. The way this color information was added to the black and white signal was by using a sine wave. This contains the color burst reference, which is off-screen right after the sync pulse. The sine wave, during active picture, has different phase angles and amplitudes to get different colors. The Vectorscope decodes this portion of the signal to provide us color information. It's important to remember Vectorscope controls, like all monitoring equipment controls, do not in any way affect the video signal itself. It's a bit like painting. When I dab paint on the canvas, the paint already on the brush is similar to the signal. If the paint has a lot of yellow, I can't change the color unless I go back to the palette, which would be like going back to the original source signal. Now, let's take a look at some basic Vectorscope functions. The Vectorscope graticule was designed to be used primarily with color bars, so we'll use this signal, which has known parameters, and take a look at the display. Reading the display is fairly simple. Each box represents a color of the color bar signal. They represent primary colors, red, green, blue, and secondary colors, cyan, yellow, and magenta. The graticule is the scale used to quantify the parameters of the signal under examination. And the trace represents the color portion of the video signal. Some Vectorscopes, like the Tektronix 1720, have these two boxes, which are used for two-channel audio measurements. But for now, let's review the basic controls which can be found on most Vectorscopes. Input controls typically consist of input channel, reference, and mode selection. The gain variable knob is used to expand the trace during precision measurements. It also comes in handy during white balancing, which we'll perform later. All the display controls are self-explanatory. Focus, scale illumination, and intensity. The phase knob adjustment is critical when setting up a Vectorscope. The color burst vector must be aligned in the 9 o'clock position with the graticule's horizontal axis. Here's the black and white photo we looked at earlier. Remember how it looked on the Vectorscope? Now we'll bring in color to illustrate how it affects the Vectorscope as well as the waveform. Here's what another shot would look like on the screen and on the Vectorscope, ending up all red. If a shot were another color, say blue, the scope would look like this. If the shot were green, like this. Remember, each dot corresponds to a color, so full spectrum pictures look something like this. Now that you have a basic understanding of how the Vectorscope works with color, let's see how we can use the Vectorscope in the studio. One of the most fundamental and critical operations in a studio is system timing. Whenever you combine one source of video with another, each source must be timed together, such as cameras using camera control units or time-based correctors for VTRs. If your system is not properly timed, you will get horizontal jumps or color shifts. Here are the basic components for a synchronous system, which is also called a Genlock studio. A camera, a couple of VTRs with time-based correctors, a switcher, waveform monitor, Vectorscope, test signal generator, and a master sync generator. The master sync generator is used to create black burst outputs, which are needed to synchronize all the components of the system. The reference signal is the timekeeper, much like a master clock is for a school system. All the other clocks are locked to the master clock. So when time is changed on the master clock, all other clocks change simultaneously. It keeps the clocks in sync. A similar kind of adjustment is done in the video studio. In the studio, the process involves setting the output of each piece of gear in the system so that horizontal sync pulses and burst phase line up with the reference signal. This information is found off to the side of the image. On the waveform monitor, we'd be looking at the horizontal blanking interval. On the Vectorscope, we'd watch the color burst. Timing the video system prevents horizontal jumps or color shifts in the picture when switching between video sources. Now let's perform a system timing. With the waveform monitor and Vectorscope connected to the program output of the switcher, select a signal source reference on the switcher, usually the black signal. Make sure both the waveform monitor and Vectorscope are set to external reference. This makes these units reference to the same signal the whole studio is using as a reference. Using the waveform monitor's vertical position control, move the sync pulse leading edge so the halfway point falls on a graticule marking on the horizontal axis. Use the horizontal position control to place the leading edge of sync on a major timing mark. It should look like this. This position will serve as a reference point for all other inputs. Now, use the Vectorscope's phase control to position the color burst at 9 o'clock. Remember, don't adjust the waveform monitor or Vectorscope controls. Use the switcher to select one piece of equipment to be timed. In this instance, we'll use video camera number 1. Adjust the horizontal phase control on the input source, camera 1, so the sync pulse leading edge is at the reference position previously established, like this. Now, viewing the Vectorscope, adjust the SC phase of video source 1 to set the color burst at the 9 o'clock position. Sometimes there are 2 phase adjustments. If so, adjust source first, then the fine, to the precise burst alignment. When they are aligned, you've completed timing on video source 1. To time the whole studio, you would repeat this procedure with each piece of equipment. Having the equipment properly timed will ensure your input transitions are clean. Now let's talk about TBCs. Time-based correctors are an important part of the timing and genlock process since they stabilize the output of VTRs. For example, TBCs remove signal timing errors caused by mechanical jitter. It's the TBC itself, not the VTR, that is timed to the system, thus system timing. Many VTRs have TBCs built into them, and they're treated identically as separate units. TBC adjustments need to be checked, if not readjusted, every time a different tape is played back. That's because video levels and hues recorded on tape sometimes differ from facility to facility and VTR to VTR. These differences can be adjusted for by playing back color bars. In fact, that's why we always record about 1 minute of color bars at the beginning of each tape. Here's how to make the TBC adjustments. First, on the waveform monitor, check Setup or Black level. It should be at 7.5 IRE. Next, adjust Video Gain, which is the brightness and chroma or color of a signal. Make sure the 100% white level coincides with the 100 IRE. Now, on the Vectorscope, make sure the color burst vector is correctly positioned on the graticule. Then adjust the hue controls on the equipment under test to rotate the dots into or near their graticule boxes. Finally, check chrominance levels. If the dots are beyond the boxes, the chroma amplitude is too high. If they fall short, it is too low. In either case, adjust the chrominance gain control on the VTR to place the dots in their boxes. That's how simple it is to make TBC adjustments. Just remember, TBC adjustments must be made while playing back a recorded color bar signal. Have you ever completed a shoot and realized you used the wrong filter? Like shooting outside with an indoor filter? It happens. This is what it looks like. And here's how it appears on a Vectorscope. It actually seems like a white balance problem with too much blue. Here's how it would look with the proper filter. White balance is the process of balancing the camera's red, green, and blue channels. By now you've probably figured out there is a difference between electronic visual reproduction and other visual reproductions. Painting, for example, is a subtractive system. When you mix the primary colors, you get a dark brown or black. Video is just the opposite. It's an additive system. Mix the primary colors in the approximate amounts of 30% red, 60% green, and 10% blue, and you get white. Now let's check the white balance. First, be sure to connect the video camera signal to the Vectorscope input. Next, point the camera at a white reference. Use the variable gain knob to expand the trace. Remember, the center of the display is black and white, so we not only get color information, but can also see if there's no color information, which is useful during white balancing. Then press the camera's auto white balance. Here's how the signal will appear if the camera is working properly and the white balance is correct. After checking for white balance, you must check for black balance. When you press Auto Black Balance, the camera will cap its lens. On some older cameras, you might have to manually cap the lens. If the black balance is correct, you'll see a fuzzy spot in the center of the Vectorscope display, again indicating no color information. Many times in a studio, you'll want to color match two cameras. This is accomplished by performing a manual white balance. Start by pointing two cameras at the same white reference. Adjust the iris on each camera to match luminance levels on the waveform monitor. If a color channel in a camera is out of balance, the fuzzy spot on the Vectorscope will be over toward the corresponding color's graticule box. To fix this problem, you must go back to the original source and adjust the blue, or in this case, the red gain on the camera control unit. It's a good idea to never touch the green control. This can create major color balance problems. Adjust these controls until the fuzzy spot is at the graticule's center. Once you've used the Vectorscope to match both cameras, you can pull the cards and fine-tune colors of the scene. The Vectorscope also comes in handy when you're trying to identify colors. This works particularly well when you need to generate a background for a scene you shot, say, a week ago. And now you need to match the color. With the Vectorscope and the waveform monitor, it's easy. Adjust the background luminance, chrominance, and hue controls. As you can see, a perfect match is assured. Proper use of the Vectorscope, along with the waveform monitor, allows you to accomplish many important production procedures. Having a system that is timed, with properly adjusted TBCs, and cameras that are white balanced and matched, lets your audience enjoy the beautiful and colorful images you've worked so hard to create.
Tektronix offers an extensive selection of documentation and videos covering test and measurement methods. To further expand your knowledge, contact your local Tektronix representative for more information or call 1-800-TEK-WIDE.